one of these Blackboard talks, which I have to get used to, but nevertheless, sort of, actually, it's, in terms of preparation and transmission, I think actually it's a very good idea to have such Blackboard talks. So this will be on nonlinear fluctuating hydrodynamics. Well, maybe I should say that, of course, there are original articles, but I wrote a fairly long contribution to a volume in lecture notes in physics, which is going to appear. I mean, that's Stefano Lebri, who is sort of the editor. And but the article is already on the archive. I mean, so you know, anyone who wants to have more details, I mean, that's presumably. I mean, you can look at other things, but I mean, that's maybe a convenient thing. And you know, what I'm going to lecture here, to some part, also reappears in this written up notes. And since it's a you know somewhat longer enterprise, let me sort of tell you what I'm trying to do. I mean, so I want to look at discrete nonlinear 1D wave equations. Okay. And of course, you know, people from dynamical systems, I mean, they do a lot of this. I mean, but they always look at zero temperature. I mean, you look at the wave field at zero temperature, then you make some excitation. You want to see solitons, you want to see scattering of solitons, and all kind of things. So that's a huge area on which I'm not going to say anything. I mean, this will be always at positive temperatures. And in fact, you know, since we have a temperature anyhow, it will be, I mean, it's not exclusively restricted, but the main focus during this talk will be always really in thermal equilibrium at positive temperatures, but of course studying the equilibrium dynamics. Okay. And there will be two running examples which I want to do. I mean, so the main part will be anharmonic chains, which is a particular class of such wave equations. And to have a contrast, I will say a few words about what is called the discrete nonlinear Schrödinger equation. And you know, when I look at my notes, and if I look at how much time I have, presumably, you know, I will not be able to say very details about this particular system, but there will be, I guess, on Friday a talk by Manas, I mean, who's going to explain a little bit more about the you know, some further features about the DNLS. Okay, and well, what is the goal? I mean, the goal of this whole business is, of course, the anomalous transport in one dimension. I mean, this is our 1D systems. I mean, so the anomalous transport, which of course you know very well. And which manifests itself already when you look at these equilibrium time correlations, and the whole goal is to give some sort of theory which explains this anomalous transport, and this will be this nonlinear fluctuating hydrodynamics. So I'm not going to develop this theory sort of in abstract. I'm sort of I will talk a lot about these models, and then I will explain how I can sort of set up the appropriate nonlinear fluctuating hydrodynamics. I will say a few words about how one is actually sort of at least get some sort of understanding of these systems. I mean, since it's nonlinear, it's complicated and it's not so immediately clear how much we can say. But I mean, this will be part of the lecture. Okay, so let me start with some sort of personal introduction. I mean, this is. I should write this a little bit larger. I mean, so this is long time tails. Of course, history of statistical mechanics. And so, I mean, this is concerned with classical fluids. In thermal equilibrium. In dimension D, so I have a general dimension with maybe 3 dimensions, but arbitrary dimension at the moment. And one thing which you would like to know is you look at, let's say, something like an energy current correlation. So I mean, let's say an energy current correlation. Okay. So this is an energy. So it's I mean, typically when one looks at the total current, so somehow the spatial part has been integrated over, and so this is just a function of time. It's a total current, energy current correlation. Okay, and well, one question is, I mean, how does it behave? And you know, this is a fairly difficult object already. I mean, you're in equilibrium, but you have to solve the dynamics in order to say something about these correlations. And the only sort of method which sort of was available, you know, a long time ago is just kinetic theory. So you basically look at the Boltzmann equation and you look at the linearization. And from this linearization, you can get some information about this energy-current correlation. And the result of Boltzmann was that it sort of has an exponential decay, right? And so since this was the only theory which was around, I mean, people, this is true at very low density, and simply people assumed that it would be also correct at higher densities. But so now I'm in the year sort of something like 1970. I mean, you know, sort of approximately around this time, you know, you could do the first sort of computer simulations, and you realize, I mean, from, you know, already from the first pictures, you could see that, you know, the idea that it should be exponential decay was not a very good approximation, and it looked much more like a power law decay. And so eventually there was some theory, and people sorted it out, and what everybody believes now, and which is sort of reasonably well confirmed, is that you see a power law which goes like the dimension over 2. Yeah. So there are many names to be mentioned. I mean, Alder and Wainwright did the first simulations, Eddie Cohen, Ernst. I mean, many people worked at that. I mean, Henk also contributed to this thing, and so many people worked on this topic. Okay. Now, there's one shortcut. I mean, this is why it's sort of connected to this thing. I mean, you can try to understand this on something which you can find in the Landau-Lifshitz book. Which is called usually fluctuating hydrodynamics, but one should remember that it's linear fluctuating hydrodynamics. So it's basically a standard Gaussian fluctuation theory, which is complicated only by the fact that, you know, we have several conserved quantities, and sort of the details are a little bit messy, but the principle is extremely simple. I mean, it's just a standard Gaussian fluctuation theory. And so you can sort of try to use this Gaussian fluctuation theory in order, for instance, to compute what would be the decay of the energy current correlation. And if you use this theory, you know, the way how it's written in Landau-Lifshitz, I mean, you will find a decay which goes like a delta function. Okay, so you know, this is a macroscopic theory. So this means, in some sense, you know, on that large scale, it's really more like what you would sort of interpret as an exponential decay. Okay. All right, so that's fine. But now, the observation at the time was that if you include perturbatively nonlinear terms, I mean, you see, this is a linear theory. These are linear Langevin equations. And now, of course, the true system, you know, has nonlinearities. I mean, you know, the currents are nonlinear functions of the conserved quantities. And so if you add sort of nonlinear terms, I mean, these are, you know, basically sort of do a Taylor expansion. So nonlinearity, during the whole lectures, I mean, what means nonlinear is just sort of quadratic, right? I mean, you want to go beyond the linear terms, so you will find quadratic terms in your equation. So you do second order perturbation theory. Which is, you know, straightforward. I mean, there's nothing very difficult about it. And what you find is that you find that it really goes like t to the minus t over 2. And you also compute all the prefactors, and it just fits perfectly with sort of, you know, more sophisticated type of theories. Okay. All right, now you look at the result, and now you see that if I take the dimension 3, then it goes like t to the minus 3/2, and then it's integrable, which means that you have a finite transport. And somehow implicitly in this whole derivation, you assumed already that there was a finite transport. And so everything sort of works well. And in 3 dimensions, you would think that this sort of somewhat simple-minded theory actually sort of of course, it doesn't give you all the details, but it gives you sort of the most important detail. It sort of computes the decay, including the prefactors of these carbon correlations. Now you look at 2 dimensions. I mean, that's, of course, where people were excited about, because it sort of goes like 1 over t, and so you have some mild logarithmic divergence, and of course, you cannot completely trust in this anymore, but, it's such a small violation that you would think it's, so no order, I wanted to say, that's right, okay. It's such a small perturbation that, you would think it's sort of still more or less okay. Of course, conceptually was sort of an exciting thing to notice that there's something sort of strange going on in 2 dimensions, but, in the usual parlance, I mean, this would be sort of the upper critical dimension, and it's still sort of more or less okay. But if you go to d equal to 1, I mean, then, this idea of doing perturbation fails totally. And, even this sort of naive extrapolation to go to, saying that it goes like t to the minus 1/2, I mean, there's just no reason to believe in that result. In fact, there's a very early contribution of, I mean, if you look there's a review article by Recevoir and Pommeau about this topic, and they have sort of like half a page where they point out already that presumably it will not be t to the minus 1/2, but there should be sort of like more like a t, like t to the minus 2/3 or so. But I mean, this was a very, I mean, it's non-reproducible argument, I would say, but they had already sort of more or less the right intuition, okay? And so, I mean, the main point, I mean, this is why I want to emphasize the nonlinear of these lectures will be that since we are working in 1 dimension, I mean, we have to develop a non-perturbative theory, okay? And so there will be sort of, in some sense, 2 parts of this thing. I mean, first of all, I have to sort of, link it up. I mean, how do we set up, this nonlinear fluctuating hydrodynamics, and then the analysis cannot be based on perturbation theory. Okay? And so we need some replacement of perturbation theory, and this will be sort of presumably what I'm going to talk about tomorrow. Okay, so today, I mean, I'm sort of trying to cover, sort of basically, hopefully arriving at what are the appropriate nonlinear hydrodynamic equations for that system. Okay, and tomorrow there will be some analysis of these equations. Okay, so now let's see what I prepared here. Okay, so let's do another chapter here. So we are in the 1 dimension, okay? So let me talk a little bit about these anharmonic chains. Of course, this is sort of fairly elementary stuff, but maybe, just to get accustomed to what I want to do, I mean, I think it's useful to spend a little bit on time of this and not simply to assume that people have seen it already. Okay? So let me start from a 1-dimensional fluid. I mean, so I have the usual Hamiltonian kinetic energy plus potential energy. Okay, so there will be some of I. So there will be some interaction potential. Qi is mu J. So this would be a 1-dimensional. So here my P's and the Q's, I mean, they are in I. Well, maybe the Q's, maybe I want to put this on a ring, but at the moment I don't really sort of think too much about boundary conditions, and so. I see you're listening. Good. P squared. Yes. Okay. Good. All right. Yes. No. I don't want to have. Well, maybe P absolute value would have been also interesting, but no. Okay. All right. So this is what one usual thing, and so I assume short-range potentials. I mean, if I would look at the equilibrium state, I have exponentially static correlations. I mean, so it's from a equilibrium point of view, I mean, there's nothing sort of particular sort of exciting about it, but it's sort of a nice fluid system. But now there's sort of one observation is that if you, okay, so the point is that you still have to sum over all particles here, and when you do numerical simulations, that's a fairly cumbersome thing to do. And in fact, I mean, maybe. I say this and hope maybe, somebody from the audience will correct me, but the point is that eventually we will have to rely, quite extensively on numerical simulations, and nobody actually has sort of done a complete simulation of a true one-dimensional fluid in the sense that, you really take into account interaction with all the other particles according to this prescription. It's just numerically expensive, and so one sort of makes this simple observation that if you take a potential which has a hard core, so maybe here I have a hard core, which I don't know, maybe that's A here, and then I take a short-range potential, some smooth potential. Well, I could have some wiggles if you want, so maybe something like this. Could also become negative anyway, but the range is sort of bounded by 2A. Then you can see, because of the hard core, that in fact this sum actually degenerates into a sum over nearest neighbors, and that's of course simplifies a lot. I mean, so for such type of potentials, you can write your Hamiltonian as a summation over J, 1/2 Pj squared, and then you sort of think of this as a V of Qj plus 1 minus Qj. Okay. So that simplifies, because now you just have to look at your neighbors, and you don't really have to do the sum over all other particles. And this is what I'm going to do all the time. Okay. Now, once you're at that stage, and you write down the equations of motion. I mean, so you have Q double dot is equal to the forces. I mean, so it will be V prime of Qj plus 1 minus Qj minus the V prime of Qj minus Qj minus 1. Okay. Then I want to think of this. You can also think of this, rather than thinking of fluid, you can think this of like a discretized wave equation. So, this is sort of a discrete version, discretized. Well, I mean, you do the obvious thing. I mean, you think of this as a wave field, and so you have sort of something like the second derivative of u. I mean, that's just this object here. And then this you think of dx of v prime of dx of u. Right? I mean, so this is your continuum wave equation. And in case this would be a harmonic potential, then this would be linear, and then you have the ordinary linear equation, wave equation. But in general, it will be some nonlinear potential. And then, once I'm on that level, then of course, I can allow for a much more general class of potentials than which comes from this construction. So, you can think of potentials which so here is my V, and here's my X, and you can think of a potential maybe like this, or you can also think of potentials which sort of maybe increase and then look like this. And so, the picture which you sort of should have in mind is that I have here sort of the set of all potentials, and here I have maybe the fluids, which could be sort of a more generic short-range type of potential. Then you have this sort of special type of potentials which have an overlap. And here you have sort of the anharmonic chains. Okay? And I will sort of continue to forget about the fluids, and will work sort of in the class of anharmonic chains. So my Hamiltonian for the rest of these lectures will be always exactly of this type. And now you may wonder a little bit, what type of potentials can you actually allow? And well, we will see in a second. But basically the type of okay. So let's leave this for a second open. I will come to discussion. I mean, what kind of potentials we can put in here. Okay. All right. So now the next thing what we want to do is we want to maybe write down equations of motion in a slightly different way. So let's see, what do I want to do? Okay. So let me sort of rewrite this in a slightly different way by introducing the stretches or the free volumes. I'm just sort of exploiting a little bit the fact that it just depends on nearest neighbors. And so I want to introduce, what I call Rj, which is simply Qj plus 1 minus Qj. Okay? And now I'm going to write down the equations of motion for this one. And so you see that the ddt of Rj, well, that's easy. I mean, that's just, okay, so my mass is here always equal to 1. So I talk about momentum and velocity okay. I think I really call this mostly momentum, but you see that the momentum is same as the velocity here. So anyway, so here you get the Pj minus Pj plus 1 minus Pj. Okay, then you can look at the rate of change of the momentum. Well, this we have written up here already, but you see now I can introduce this variable, so I get Rj minus 1. And so you see that I've written this already in sort of conservation form. I mean, these are, okay, so, you know, if I do this discretization, it means that, you know, having a wave equation, having a discrete wave equation, I mean, you know, I have a sort of an underlying lattice. I mean, so here is my lattice spacing. Okay, maybe this is 0, and I look a unit lattice spacing, and at every point I have sort of sitting these two variables, right? I mean, here I have the Qj. Well, okay, so here I have the Q0 and P0. And when you look at these equations of motion, you see that I have already discovered two conservation laws. I mean, one is the stretch. I mean, because, you know, on this side it's sort of written as a difference, and therefore, you know, on the lattice it would be just a local conservation law. I mean, local. I use this word local conservation law just to emphasize that you know, it really comes from a structure like this, in the sense, you know, when I want to look. If I think of if I want to think of various, you know, a few lattice sites like this one, and you know, well, maybe I should do this differently. I mean, I look at the small volume, you know, always the underlying lattice, and I'm asking myself, how does the sum over the Rj's in this little interval change? I mean, then it will change only through the boundaries. I mean, this is what I mean by a local conservation law. You know, if you have a global conservation law, then it's just a quantity which is conserved by the dynamics. But here actually we have a little bit more of information. I mean, you know, it's really that there are currents and there are local currents, and you know, the change is sort of, you know, the way how this changes is through the currents at the two boundaries. Okay, so here I have two conserved quantities, and well, I mean, since it's a mechanical system, you would think that there should be another conserved quantity, which is the energy. So I have to first define for you what is the energy. Well, I mean, if you look at this Hamiltonian, then you see that here I have nothing else than the Rj sitting. And so, you know, this is just the sum of one particle Hamiltonians, and so it's clear that what I should define, okay, maybe I should have done this differently. So what I should define as the local energy is, of course, nothing else than the kinetic energy plus the Rj. And now you can figure out what is the change in energy. And of course, it must also satisfy such a type of local conservation law. And what you will find is that you will find that this is Pj plus 1, the force at Rj minus the Pj times V prime of Rj minus 1. Okay, so I have actually three conserved fields, and there's a special structure somehow that, you know, I mean, so here the current is the momentum, here the current is the force, or minus the force, and here the current is just the product of them. I mean, that's sort of a structure. You see, I mean, this is just the product of these two objects up there, and that's sort of a specific feature of these anharmonic chains. I mean, it will also actually, in some sense, reappear in the DNLS, and that sort of allows for a lot of sort of simplification compared to the most general case. All right, so we have three conservation law, and now comes sort of a similar clause what David had in his lectures. Had in his lectures, namely what I will assume. And of course, it's a very implicit assumption because nobody knows how to check this, but I will assume it anyhow, namely that there are no further. I mean local. When I talk about conservation laws, I mean local conservation laws. I mean, if this, you see, this is sort of like a global assumption, which you know, you give me the potential. I have no way how to check, but you know, it's believed to be sort of rather generically true. So I want to avoid the integrable systems. Okay, so I could also have said that, you know, I want to make sure that these systems are actually non-integrable. One definition of non-integrable. Other cases, but in particular it also includes, so this is the harmonic. It would exclude the total lattice, which is e to the minus x, maybe a linear part, but I mean this, okay. Okay, let's just write e to the minus x, so this is the total chain. And maybe fewer others. So in this big space of potentials, so there will be this somehow. I mean, there are simply these exceptional points. I mean, the exponential potential and and the x squared. They are simply there. And there's nothing to do about it. But they will behave totally different from what I'm trying to tell you, right? I mean, so I clearly I have to make this assumption that there are no further conservation laws, and somehow it's believed that. You know, maybe there are others which nobody has discovered, but you know, people have looked already for many years, so maybe it's not so easy to find anymore. And we simply don't have any examples, you know, which you know, have, let's say, you know, given that particular structure, we don't know any examples where we have 25 conservation laws. 25 conservation laws would be okay for me, but you know, I don't want to have sort of a number of conservation laws which are proportional to the degrees of freedom. Okay? But we don't have any examples. I mean, you know, we only have examples of this type, and we don't have examples where we have 5 conservation laws. Would be still okay. Okay? So let me just assume this from the beginning. And of course, you know, there's this issue. I mean, the same thing what David was saying in his lectures. I mean, I could be very close to one of these integrable systems, nevertheless satisfying these assumptions. Then, of course, something must be happening, right? In the sense that, you know, you would think that on a certain time scale, the system sort of is confused and sort of it might think that it's actually really a harmonic chain, but actually it's not a harmonic chain. And so there will be crossover phenomena and all kind of complicated things, which, of course, at the very end of the whole story, one would have to sort of to reconsider. But I just want to emphasize that whatever I'm going to do, I mean, this is sort of in the back of my mind. And of course, you know, I want to have the system sufficiently chaotic in some sense. And anyway, so I'm not going to repeat this, but it's you know, you will see that implicitly such kind of addition will appear. Okay, so now having emphasized this, I mean, then we can maybe sort of proceed. Maybe one thing is, since it's an important point, and maybe later on I'm not going to emphasize. You see, when I write down this nonlinear fluctuating hydrodynamics, which will take a little while, then you will still see that if I then assume that the potential is quadratic, then you see already in the equations that you know, they are somewhat special. So the nonlinear fluctuating hydrodynamics can see the difference between the generic and the harmonic case. But if I look at the total chain, it will not be able to discover this distinction, will not be able to discover that there's a difference between the total chain and the more generic case, right? I mean, so you know, the fact that you know, I assume it, but you know, I cannot see these exceptional cases on the basis of nonlinear fluctuating hydrodynamics. Anyway, so we will see. So I just want to emphasize that we are always in the non-integrable case. Okay, so the next thing what I want to do is I want to look at the equilibrium measures. Well, that's very easy. I mean, you just put e to the minus beta h. But now remember that we have actually not only one conserved quantity, but we have actually 3 conserved quantities, right? So of course there will be the temperature, but there must be 2 other sort of Lagrange parameters which appear in my Hamiltonian. And so let's just sort of write this down. So we have a 1 over c e to the minus beta. Well, there is the summation over j. Now, there will be, first of all, something which is the average momentum. Since it's in the Gaussian, I mean, sort of, you know, I don't have to introduce too many different symbols, but anyway, I mean, it will be a shifted Gaussian. Then, of course, there is the arched potential, and then there must be a Lagrange multiplier which corresponds to the stretch. Okay, and so I just put here the P of Rj. Okay. So we have 1, 2, 3 parameters in our equilibrium measure. But then nevertheless, you know, it looks very, very neat, nothing very problematic. That's one of the advantages of these anharmonic chains. You see that, you know, it's just independent. It's just a pure product, right? Now the P, okay, so first of all, let's record this. So Rj and the Pj's are independent. Okay. And the Rj's are just, you know, the Pj's have a distribution just a shifted Gaussian. And for the Rj's, I have the distribution e to the minus beta b of x plus p of x dx, right? I mean, 1 over c dx. Okay, so we are in a very sort of simple situation. Okay. Now, okay, so beta, of course, is the inverse temperature. What is P? Well, we have to do one little computation, which I'm not going to do, but which is a simple partial integration. I mean, you note that the following identity, that P is minus the V prime. Let's see, so okay, there's a question of which notation I'm using, but I want to use the notation that you know, this average always means the global equilibrium average. Okay, so let me just put in here sort of, let's say, the R0. Okay, and then you know, since position, I mean, since stretches and momenta are independent, I can forget about the Gaussian. I'm just doing this one single integral over R0. And you know, when you do the partial integration, you find this simple identity. Okay. Well, so this means that the P is nothing else than the average force between, you know, particle with label 0 and 1. And so this is something which we would call the pressure. And so I refer to the P here always as the pressure in my chain. So, you know, if I start stretching the chain, then there will be sort of a somewhat different pressure. And okay. People also use the negative of this. And anyway, so let me just take this convention and this, you know, there's a question whether I put here plus or minus. Anyway, so we have 3 parameters, the mean velocity, we have, of course, the temperature or the inverse temperature and the pressure. Okay. Now, from this, you can also see what type of potentials we want to use. You see, I mean, somehow, basically, what I want to have is that the partition function is finite, right? And so you know, there are basically 2 generic cases. I mean, one case is that it looks like this. This is sort of like so here, for instance, this would be, let's say, something like the FPU potential. I mean, this is Fermi-Passer-Ulam, so this sort of famous sort of first paper on numerical simulations, and first time when people sort of, you know, when simulated such kind of nonlinear dynamics. So this is a potential of the type V of x equals 1/2 x squared plus alpha x cubed plus beta. I guess there are prefactors. Okay, I mean, okay, I do it right. I mean, so beta over 4 x to the power 4. So this is the Fermi notation. So it's just an anharmonic potential. And then in the FPU experiment, I mean, they sort of on the very early computers, they simulated, I don't know, 16 of these nonlinear oscillators. Anyway, so this would be one case. In this case, of course, the P can be completely arbitrary, can realize any pressure in the system. And but you can also allow, like the Toda chain, you can allow, for instance, a potential which looks like this. But then you cannot use an arbitrary pressure because, you know, you want to have this integrable, so you must sort of add a linear term in order for avoiding the divergence of this case. I mean, so in this case, you have to choose a positive pressure, right? So that's already more or less generically the type of potentials which you can admit, right? I mean, they have to, they should be bounded from below, and they have to sort of go up to infinity, either for minus infinity or plus infinity, right? I mean, if I take a potential of this type, which would think natural for fluids, is no longer allowed in this game. It doesn't have a finite partition function. People nevertheless simulate this and then make all kinds of claims. I mean, people put in the Lennard-Jones type of potentials here, and so one has to be a little bit careful, right? But basically, a finite partition function dictates for you what type of potentials you allow in this theory.
We can allow that at large positive pressure. Could you even allow such a potential if you have pressure or not?
Yeah, no. I mean, you have to first give me the potential, but you see, for this type of potential, there's no pressure which I can choose. Well, how can I make partition function finite? No, but for soft spheres, I have a hard core. I mean, then it looks like this. I mean, that's of course okay. But if I take a smooth potential, which no, you cannot. Well, if you no. I mean, not on the level of this model. You see, if I take so let's be very concrete. I take a potential which looks like this. I mean, this is my v and this is my x. This is a potential which is not allowed because there's infinite partition function.
Not at zero pressure.
At any pressure, it is at any pressure. Okay. Let's look at this partition function. It's the integral dx e to the minus v of x, and now of course you want to add some pressure, but it doesn't help very much. We're always with infinity. No, I insist. I mean, this is not an allowed potential in this theory. This is infinity. This is infinity for any.
Negative volume. Physically, what it'll do, it will compress to infinite negative volume.
Yeah, sure.
Which is nonsense.
Yeah, okay. I'm not objecting against particle interacting via this potential. I mean, that's a perfect fluid, and I'm just saying that within that particular theory, the type of potentials which I can allow, I cannot allow such type of a potential. We'll always have infinite. Okay. Anyway, it's not the point. I just want to say that there is a restriction on the type of potentials which you can admit. Okay, fine. Okay, so the next thing, we should think for one moment about boundary conditions. I mean, so I haven't really talked much about boundary conditions, but it's sort of more or less clear from what you want to do. I mean, you see, the only thing which maybe is not immediately totally obvious is, what type of boundary conditions you want to use. So maybe I should say, no, maybe I want to say, okay, so maybe one word about boundary conditions. So, mentally I'm always thinking in terms of periodic boundary conditions. But of course, in these variables, I mean, in the momentum variable, it's sort of clear, it's the usual periodic boundary conditions, but I'm also thinking in terms of periodic boundary conditions with respect to the stretches. Okay, and so maybe we should do one little thinking of what this means in terms of the original positions. Okay, and so you see that in terms of the original positions, I mean, so I want to assume that the Rn plus 1. Okay, so let's take a lattice which is j going from 1 all the way up to n. And periodic boundary conditions in terms of the lattice would mean that the Rj, that the Rn plus 1 is equal to R1, right? I mean, that sort of would be the natural boundary condition. Okay, and now if you think about what okay, and then I will have a microscopic, so and then I want to do a constraint the RHA, if I think of sort of a more, rather than sort of a microcanonical restriction, rather than this sort of canonical one, then this would be some particular value, which is n times L. Yes. Okay. So I'm going too far off. Okay. Okay. So I can. All right. Slightly bigger. Okay. All right. But I see already that from your side, I mean, this angle is very. So why don't I just erase here? I mean, this is something which I don't need, and then start. Okay. Maybe I can start a little bit over here. Yes. Okay. All right. So in the meantime, you can think about this periodic boundary condition. So now I'm thinking of doing a microcanonical ensemble, and I want to do these boundary conditions. Okay, so the Rn plus 1 is equal to R1. And now I want to do the microcanonical constraint, which would be j equal 1 up to n. And then I have Rj, and then I put this n times L. So this would be dual for the pressure, right? And now I just want to think of what this actually means in the actual positions. And you see that if you simply insert my, if you just simply insert, then you see a telescoping sum. And then you see that the conditions which you get for the positions are actually that the Qj is equal, let's say, plus n is equal to Qj plus, I mean, the telescoping sum is somehow fixed by this value is equal to NL. And so if you want to sort of think of this pictorially, then what I'm actually sort of doing here is that here you have maybe position 1, 2, etc. n, and then I'm sort of imposing a slope in terms of the Qs. I mean, so this n, and then there's n plus 1, and this n plus 1, so here I have them all in between. And this n plus 1 has to be equal to Q1 plus NL. I mean, so this is here Q1 plus NL. Okay. So, when I talk about periodic boundary conditions in the RHAs, it just means that in terms of the Qs, I'm imposing such type of a nonlinear slope. Yes, slope. So L is the microcanonical parameter which is dual to the pressure. So if I would do a microcanonical simulation or a microcanonical computation, then what I will do is I would fix the value of this conserved quantity, just like the other ones. You see, I could also fix the value of the energies. Where are the energies? Here are the energies. I could value the total sum of the PJs. That would be a completely microcanonical prescription. And the only thing which I want to say is that if you sort of actually think in terms of the Qs, I mean, then it means that I have this kind of shifted boundary conditions with respect to the Qs. All right. Okay, so I think this is already, let's see, how am I doing? Not very well at all. Okay, so I guess, maybe I should do this rather quickly, actually. So I want to briefly introduce the other system. Maybe I don't do it at that detail. I mean, it's not really needed. But I want to sort of keep this sort of as a contrast. So here is a discrete nonlinear Schrödinger equation. Maybe I should, sorry, I mean, I forgot. Such a long blackboard. I mean, so let me sort of erase rather than shifting outwards. Okay, so NLS. Okay, now you have a wave field psi j, which is actually complex, and j is in my lattice C. Okay, and you have an energy. I mean, let's say for n size this periodic boundary condition, so it's 1 up to n, and you have sort of like this gradient term, the nearest neighbor coupling. So I'd say absolute value squared. And now you have a potential term which is on-site, which is G G is the coupling, and I take psi j power 4. And I want to have this coupling to be positive, which is usually called the defocusing case. I mean, you can study the system also with negative G. I mean, that's an interesting question. But it's totally outside. I mean, you will have totally different behavior. Anyways, so this is my Hamiltonian, and of course the equilibrium measure. So in this case, you will have. Well, maybe I first write down the equations of motion. I mean, so you can think of either commutation, either sort of Poisson brackets between psi and psi h. And I mean, you can also think in terms of, I mean, the position, the canonical position momenta are the real and imaginary part of this wave function of the psi. So, you know, if you just write down the usual Hamiltonian equation of motion, then it ends up to, so here's the I. I mean, this is, okay, I mean, well, okay, yeah, here I used only J as the index. I mean, so this is square root of -1, and then there will be 1/2 the discrete Laplacian. I mean, let me, minus 1/2. So this is a discrete Laplacian at J, and then there will be this potential, the nonlinearity, the cubic nonlinearity, which is on side psi j squared times psi j. Okay, so this is why it's called nonlinear Schrödinger equation, because you know, when you write down the evolution equation, well, I mean, already from the energy you can see this, and the evolution equation, of course, is the usual Schrödinger equation, which usually would have a linear potential, but here it has this added nonlinearity. Okay. Well, I mean, so yeah, so these are here the wave field is complex, all right, and this is believed to be non-integrable. And it will be integrable, correct? It will be integrable if I would take the continuum limit. Then you have actually an integrable system, famous integrable system. That's the usual nonlinear Schrödinger equation. And you know, if I sort of follow this scheme, the next thing is what are the conserved quantities? Well, it's the same thing. I mean, you have just want to see at my notation. I mean, so you have something like the rho j. Which is psi j absolute value squared. So that's sort of maybe something like a density, but we will see. Okay, just take this you know, as a definition, and then of course there will be the energy, which maybe I don't have to write down, because you know, I mean, the local energy is just exactly what you see under this bracket. Okay, so in this case we have two conserved fields, and of course the equilibrium measures are simply e to the minus beta, the h, and then you know, we also want to, because so this is a dual parameter to the energy, and now I introduce chemical potential mu times n, and of course the n, sorry for the, okay, so there are two n's here now. Okay, so maybe I put here an extra n now is okay. So maybe okay. So let's see. I wanted to say. No, I wanted to do one more thing actually here, because otherwise you cannot even understand why I'm bringing up this particular case. So let me go over to polar coordinates by writing the psi j as the square root of rho j times e to the I phi j. Right? So this is actually a canonical transformation. So these are the rho j in this definition, and this are canonical transformation. Okay, and so I don't really have to transform the equations of motion. I can transform directly the Hamiltonian, And if I know that these are, you know, a pair of canonical coordinates, then of course for these new coordinates, I mean, you have still the standard sort of Hamilton's equation of motion. And I just want to write down for you what is the result of this transformation. So it's a minus rho j plus 1. And there's a cosine. So now, of course, all right, okay. And then I have a plus rho j. Okay, so that's your new Hamiltonian. And I just want to compare this with what we had for the anharmonic chain. So you see, if you look like this, I mean, then there are two main differences. I mean, first of all, you know, these variables here, they are not living on the real line, but they are living on the circle. The rho j's are positive. Well, okay, that's sort of maybe not so unusual. I mean, I could have also, for my anharmonic chains, I could have a potential. You see, I mean, here, if I have a potential of this type, then of course, you know, oh, okay, no, that's not a good remark. Okay, so the rho j's are positive. I'm just coming back to this. Okay, so these are the constraints, and now you want to see the analogy to the anharmonic chain, and then you discover that you know, this term. Okay, so the correspondence is really that the rho j sort of plays the role of the pj. I mean, mathematically, you see, physically, maybe that's not a very good analogy, but this is sort of really like a kinetic energy. But the point is that the rho j, I mean, these momentum type variables actually take only positive values, and the phi j. I mean, the reason why I make this analogy, because you see, this is sort of like the way how the positions entered into the anharmonic chain. It was qj plus 1 minus qj. Okay, and so the analogy is that the phi j is sort of similar to the qj. And so the phase difference would be similar to so the phase difference. I mean, the rj is sort of you know, the rj would correspond to the phase difference. Okay. But you see, it's not of course it's not perfect. I mean, first of all, you know, this is living on R, and this is living only on the circle. So that's a very important major difference. And then sort of from a technical point of view, one difficulty is that you know, the strength of the potential term actually depends also on the momenta. So you know, it's some sort of somewhat strange, but looking anharmonic chain. I mean, and if I look at the e to the minus beta h, I mean, it's not really. Becomes not really independent. I mean, you still see this nearest neighbor coupling sitting over here. I mean, here I can introduce the differences. I mean, then it looks like independent, but here I still have a coupling. I mean, so I cannot really make it a product measure. Okay, so this is sort of as a small insert, and maybe I have a chance sort of to say something more about the system as I go along. Okay, so now what is the next step? Well, I mean, now we want to do nonlinear fluctuating hydrodynamics, and what we have to do is we first have to write down what are the correct hydrodynamic equations for this system, because that's sort of the cornerstone from which the nonlinear fluctuating hydrodynamics is built, right? And so the next chapter will be okay, no, I said one thing more. Okay, no, sorry. I mean, I still have to sort of say what we actually want to study. I mean, so what we want to study are the equilibrium time correlations and actually not any equilibrium time correlation, but we want to look at those which have sort of the longest lifetime, and these are the conserved quantities. So we want to look at the conserved fields. But in some sense, once we understand the conserved fields, the picture is that then we understand sort of more or less, the long-time behavior of any equilibrium time correlation. Anyway, but what we want to study is sort of the conserved fields. And so let me maybe first write this down and then say a few general words on this. So, okay. So,
Herbert?
Yes.
So the equations for rho j and phi j, they have they actually have an Hamiltonian structure, is it?
Yeah. I mean, so this is what I said. I mean, this actually, this transformation is a canonical transformation, and so this means that when I write down the equations of motion, I can just do the usual
Hamiltonian equations of motion.
Yes. Hamilton's equation of motion. Okay, so let's see. So let me collect the conserved fields into a little vector. I mean, so I have a 3 vector, which consists of Rj of the momentum, and which consists of Ej. Okay, and now the correlation functions which we want to look at, are very easily defined. I mean, since I have 3 fields, I mean, the correlation functions will be a 3 by 3 matrix. And I typically put here this matrix, I mean, the matrix elements down here as an index. But, very often I use also a notation where I simply omit, these indices, and then I have to remember that I'm working actually with a 3 by 3 matrix, right? And that, of course, depends on J and T. And the definition is sort of the obvious one. So I take, let's say, the field alpha at lattice point J at time T. And now the expectation which I'm going to write down will be the equilibrium expectation, which has the property that it doesn't change in time, but it doesn't also change under spatial translations. I mean, because the Hamiltonian is translation invariant. I mean, it's just independent. It's identically distributed, so it's really invariant under translations. And so I can already, without restriction of generality, I can put here simply the index 0. And the index 0. And then in principle, if I'm careful, I should indicate that, of course, once I write down this average, I have fixed the value of the pressure, of the temperature, and of the average velocity or average momentum. But I mean, just otherwise it will take forever. I mean, if I'm going to write this down, and of course I will subtract the equilibrium averages of this quantity. So this is really sort of our goal. I mean, we would like to understand. So it's it's a matrix. It just depends on 2 arguments. We would like to understand how this behaves typically for large T, or maybe for both large T and large J. Anyway, so we would like to understand sort of the large scale behavior of this quantity, large scale. And the claim is that the anomalous transport, which we sort of know already for 1 dimension, will be also seen when we in the large scale structure of these objects. Okay. And the general picture is the following. So now I sort of do maybe a general picture. I mean, so here's maybe time, and somehow. What we believe, which I will not enter, but maybe it's sort of useful, sort of to see that there's a lot, in principle, a lot of information in this type of correlator, is that, I imagine that I prepare my system in thermal equilibrium, and I do a local perturbation. I mean, so, but I mean, it's sort of fairly unspecified. I mean, I just sort of bump into the system and do something without being very controlled, okay? And then the picture is the following. So here I'm sort of plotting some sort of correlation function. So it will have some behavior. But the claim is that within a relatively short time, I mean, the only thing which is left from this perturbation is its projection onto the hydrodynamic fields. Okay? So here I have already the hydrodynamic fields. And so at that moment, things will propagate according to this thing, because you see I have a small perturbation that's sitting over here. Now here I simply put it in to have a mathematical definition at time t equals 0, but physically maybe I have to wait a little time until I actually see, you know, this particular linear combination of the conserved fields at that particular time, right? I mean, but so this time sort of in this formulation is now the time 0. Okay? Now, once I'm here, now I will propagate for a very long time according to my propagator, which is computed as an equilibrium time correlation. And then at this point, I sort of do some observation. Of course, if I observe the conserved fields, then you know, there's nothing else which I have to do. But in principle, I could observe also some other local quantity. And then, you know, there's again here sort of, you know, another time span where I have to go onto the hydrodynamic projection, and that will tell me, you know, what is then. So there are two hydrodynamic projections, sort of one at the initial time and one at the final time, but in between I propagate according to this propagator. Okay? So what I'm trying to say is that once you know this, I mean, then you know actually sort of I mean, in some sense you know quite a bit more than just sort of this special correlation. But for the theory, I mean, that's fine enough. So I will concentrate myself only on the correlations of the conserved quantities. It's always, I mean, so the setup is that I'm always sort of starting the system prepared in equilibrium, and I sort of make a local perturbation. Here in this formula, I make a very specified, you know, precise local perturbation, which is given by the conserved field itself, right? But and so it might look sort of, you know, very, very special. But if I look at long time, actually, you know, that's really the quantity which carries all the information about the dynamics. These hydrodynamic projections, you see, they of course they take a little time span to be effective, but eventually, you know, it's just sort of an equilibrium type of projection, right? Okay. And so now I should the discrete nonlinear Schrödinger equation we did already. Yes, question?
So what do you mean by this hydrodynamic projection? What do you mean by this hydrodynamic projection?
What I mean by this hydrodynamic projection is that you see you have the conserved fields, right? And so I don't know which way you want to think of this, but you have the conserved fields, and so you're working well, okay, so you know, okay, so maybe I can say something not too precise. I mean, you can think of this. I mean, if I take any local observable, you can think of this sort of like a scalar product. Right, and so you know, so in terms of this scalar product, I can do a projection of any local observable onto the ones which are sitting over here. So if this is sort of my channel observable, and here I have the locally conserved fields, you know, I can. This is not completely correct what I'm saying, but basically I can do such type of projection. It's wrong what I'm writing, but you know, just for the purpose of the explanation, I mean, this is sort of what I mean by my projection, right? And so you know, basically what I'm saying is that if I wait a little, if I do an arbitrary perturbation, if I wait a little while, then eventually I only have to look at the time evolution of the conserved fields. I mean, they sort of carry most of the the long time information. Okay, maybe I can define for you more precisely, but that's basically what it is. Okay, so now we want to do, so I should want to actually get to this point. I mean, so now the next thing we want to do is the hydrodynamic equations. And in fact, it will be only the Euler equations. Okay. So they are easy to figure out, and but you know, again, it's sort of one of these background information which I simply sort of would like to explain. And so the idea is extremely simple. I mean, you assume that you prepare your system in local equilibrium. And what this means is that you have sort of this underlying lattice, and then you have sort of some variation of your conserved fields. But in a small piece, I mean, I'm thinking that this is sort of essentially constant. And so when I look at the state over here, I mean, then it looks like an equilibrium. A more formal way would be to actually look at our more formal way would be to look at our equilibrium measure. Let me do this over here. At our equilibrium measure, so I wrote e to the minus beta summation of all these terms here. I mean, the energy and all the other one, the pressure. Okay. And now simply assume that you push the beta into the sum here. So you do this for all fields, but let me just do it for the beta. So of course I can write this as sum over j beta times the local energy. That's fine. I mean, I haven't done anything. But now I assume that beta is actually lattice dependent, but it varies on a macroscopic scale. It's a slowly varying function, right? I mean, so I can put in here beta j times Ej. Now, of course, if I think of beta varying on the scale of the lattice, I mean, this is another very meaningful state. I mean, what I mean by local equilibrium, that this as a function of j has a very slow variation, as I indicated over there, right? Okay, and now, so this is one particular initial state which I can pick, and now the claim is that if I'm going to look at some time later, I will see again a local equilibrium state, but with different parameters. That's all. Okay, and the way how the parameters evolve, they evolve according to the Euler equations of that system. Okay, and so let me sort of do this in a little bit sort of more precisely. I mean, so first of all, I have my conservation laws, which is J alpha of J. Well, okay, let me leave out the T. Okay. Well, so there are two currents. I mean, this changes because it increases. I mean, you lose mass because one current is going to the left and the other one is going to the right. I mean, so this is just my discrete conservation law, which I've written already, but now I sort of write it in a sort of more convenient form. So now I have a 3-vector of currents, and we have computed them already, right? I mean, this was my equations of motion. I just sort of repeat this. So this is a minus. So for the stretch, we had minus the momentum, and then we had the force at Rj. Well, let's say the force at j minus 1, and here I had the product, so it was minus pj v prime of j minus 1. Right? I mean, so these are the 3 components of our current. Well, and then, of course, once I have this, I can sort of average this over my local equilibrium state. So I just take these equations and do an average over my local equilibrium state. So maybe actually when I do this average, maybe I should have kept the time dependency. I mean, that's maybe a good idea. Okay, and so I get ddt of this local equilibrium average alpha j times t plus the average of this current alpha at j plus 1 at time t minus Okay, so I haven't done very much. Okay, so now, well, I mean, this is the local field itself. I mean, so if I, denote the macroscopic field sort of by some new variables, I mean, this quantity sort of maybe spatially averaged, or here I think of an ensemble average, but physically it's really a spatial average over a small region, then it will have a particular macroscopic value because it's slowly varying. So, when I do spatial averaging, I mean, we'll have fixed values. So that's a law of large numbers. I mean, so let me call the macroscopic fields. I have to use a little bit of notation. I mean, so let me call them. So what they really are is really, it's a stretch. It's the average velocity and it's the total energy locally, right? I mean, so these are the three things. Now, it's hard to always sort of use these symbols. I mean, so let me just call them U1, U2, U3, and you just have to remember that when you actually plug it in, I mean, one is sort of the local stretch. I mean, it's R of x at time t, so to speak, eventually, right? I mean, but these are the three. So this, of course, I can easily compute. I mean, so what I find is that I take ddt of, so now I have U alpha. I mean, so let me write out explicitly. So, okay, so there's a partial of t, U, t, alpha of x and t. So I'm going already, to a large scale limit. And so the j becomes sort of a continuum index, which is x. And of course, the alpha stays, and the g, I have to look up in the list which g I'm using, and then it will be either one of them. Okay, so this is sort of the limit of this. Well, here you see that this is sort of like a difference. So this will, in the continuum, of course, will become the derivative dx. Okay. And now the most difficult part, of course, are the currents, because the currents are not in the list of the conserved quantities. There's something else. But at that stage, it's a local function, and the equilibrium average at time t is assumed to be a local equilibrium. I mean, of course, if you want to prove such equations, the validity of such equations, I mean, you would have to establish this, which typically would be not such an easy exercise. But here on that level, I simply assume the local equilibrium. And then, of course, this average becomes very easy, because, what I have to do is I have to compute now this average current alpha. Okay, but now, well, let's say at the origin, if I put the dependence, I mean here in the x variables, but now in a state which depends on the local equilibrium as determined by the value of the fields on the right-hand side. So I didn't introduce a very good notation for that, but I mean here I have sitting this u vector at x at t, and that's equal to 0. Okay. So these are already now my Euler equations. The only thing what I have to do is I have to sort of work out this average a little bit more explicitly, so that I can see what it is, right? And so let's do that.
What's the 0 on the current?
Because I mean it's 0 in the current is that I'm looking at the current at latticide numbers at latticide 0.
But then,
and the x dependence is sitting in here.
but it seems like if that's the usual continuity equation, shouldn't that be x equals 0 in the first term?
No, I look. I mean, okay, I'm looking. No, I mean, so here's my microscopic level. Somewhere is here my microscopic x, right? So now when I do this average here, and this j becomes simply the x in this equation.
Okay.
X is x.
Why didn't the j on the current become?
Because I shift. I mean, the question is, where do I shift that? Okay, so here's the ddx. Here, what I'm saying is that I put the x dependence into this parameter simply, right? And okay, so I mean, think of the picture. I mean, it's quite clear. I mean, so here I have sort of these things, right? I mean, so here, so this is what I mean by my x, right? I mean, that it's that part of the lattice, okay? And then, so I'm saying that at this point x, I will have a local equilibrium state with parameters, with parameters given by the values of the field sitting over here, which are these particular 3 vector of parameters, okay? Now in this equilibrium state, I have to compute the average current. Now at that point, now this is a translation invariant state, so at which point I compute it, it doesn't make any difference. So I can equally as well just compute it at the origin.
So the 0 just means any point.
Exactly, it means any point, it just doesn't make any difference, okay? All right, sorry, I mean, it's, okay. All right, okay, so now I have to do, so the main point which I want to emphasize is that in order to get the Euler equation, it's actually a very simple procedure. You have just to compute the equilibrium value of these currents, right? So in that sense, there's nothing yet complicated as transport coefficients are so appearing. It's just sort of doing this equilibrium average. Okay, so let's do this equilibrium average. Well, I listed everything, so that's very easy. I have to look at my list of my currents, right? I mean, so this equilibrium average now. Okay, this vector, I mean, it's 0, is given by the following vector. Well, I mean, so this is of course simply minus u. Okay, now this, we know that this is the pressure, right? It's the average of the force. So this is the pressure. And this one we know is just it's just the product of them, right? I mean, so this would be, something is wrong here. Do I do this correctly? Minus u. No, I think, I know, okay, so this one is, okay, so this one is the pressure and then it's times u. So here I have u times p. Okay. Now what is this? Okay, so now we have already our Euler equations, right? I mean, so here I have u, and now I have expressed the average currents in terms of the conserved fields, and here's the explicit expression, right? So it's a nonlinear equation, and of course, okay, so what is the problem? The problem is that on this side of the equation, you see, okay, so now I see I made some sort of conceptual sort of blunder a little bit, but anyway, so no, this is actually not very good. Sorry, I mean, I accuse myself this is sort of confusing, so I have to sort of repair this. I mean, this is correct, but you see okay, now this equation is still correct, but you see the average which I'm doing over here is okay. So here I really have to use the indices, otherwise it's not good. Okay, so you see the average which I really should take according to this prescription is in some sense the microcanonical average, the one which is sort of, you know, where the parameters are actually the fields. Okay, the u's, I mean, the u's are the physical fields. Okay, however, the average which I can easily do is the canonical one. Okay, so here I put p, here I put beta. So here I put p for the first component, the u for the second component, and the beta for the third component. Okay, so these objects, I mean, the u are sort of, you know, I mean, that's the correct average, and you know, I have to. But however, here I have to insert the parameters, the microcanonical parameters. So I actually I have to do this inversion from going from the canonical parameters to the microcanonical parameters. Okay, so let me sort of do this inversion sort of correctly. I mean, okay. So that's just a thermodynamic transformation, right? I mean, this is a dynamic equation. The only trouble is that I have, in some sense, expressed this in the wrong variables, right? So I have to correct this, and so let me do this sort of correctly here at this stage. Okay, so what do we have to do? Well, so we computed already here these 3 objects, and what you want to do is you want to express. So the u is fine. I mean, the u appears already over here, but you see, I have to look at the pressure. Okay, so the pressure can be expressed as a function. So the pressure. Okay, so I have the pair beta and pressure, and this will be related to the total to the stretch, and will be related to the total energy. Okay. Well, okay, maybe I write this as p beta, sorry. Okay, so this is the r is the dual variable to p, and beta is the dual variable to the energy. And now I have to express the pressure simply as a function of these two things, and this I have to do by doing this thermodynamic transformation, which I'm not going to do. I'm just sort of remind you that I have to go to these other variables, right? And so after I doing this, I will get the P as a function of R and of the total pressure, of the total energy. Sorry, I will get it of the energy. Sorry, the energy. Okay. Okay, but now what appears in these equations is actually the total energy. And so the only thing which I have to do is I have to use the fact that, the total energy and the internal energy is sort of related by the kinetic energy. And so all what I have to use now is that the E total, that's the total energy. That's the one which is the conserved quantity, which appears in this list here. That's the total energy which appears in this list. And this is nothing else but the kinetic energy, which is 1/2 u squared, plus the internal energy. So this is internal, and this is total. I mean, so that's one thing which one has to take care of. Well, okay, so then you see the variables which I would like to use is the total and the u. And so what I have to plug in here, so I put this here. So the u is okay, but the p will be the thermodynamic computed function as a function of the stretch through this Legendre transform and the internal energy. And so it will be a function of R, and it will be a function of the internal energy, which is the total energy minus 1/2 u squared. Okay, and now I have a closed equation. So you see that I have the time derivative of this conserved field is the gradient of the current. That's a 3 vector. I mean, so the current has these components. The u and the u appears over here, but this is also in the list. That's just the second component. That's this one. And the p has to come from thermodynamics. So here is where the potential, the specific potential which I'm using is actually entering. And so I have to use this pressure computed thermodynamically as a function of the stretch and the internal energy. And then I have still to do this Galilei, expressing the total energy, the internal energy through the total and the u. And now you see that all the fields which appear in the currents are also sitting over here. Okay, so this is now a closed equation. So these are the exact, I mean, of course it's a large scale, and of course I assume the validity of the Euler equation, but these are the exact Euler equations for that particular system, which actually do, of course the structure is independent of the particular potential, but the concrete nonlinearities which I put in do depend on the potential. Okay, so I hope I didn't make this too confusing. David, yes?
One step which, so down here in the energy you have the momentum times the force, right there, yeah, right there, the momentum times the force, and then you averaged it, and you just put the average momentum times the average force, and ignored any correlations.
Well, they are actually, no, they're actually not, no, I mean, the stretches and the momentum are independent.
Because it's a product measure.
Yeah. So if I put the DLNS, I mean, that of course would be no longer true. Yeah.
Right. It's because they're a product measure.
They are really product,
so
yes. So I can really.
It's zero, so you drop it.
That's right. Yeah. Okay. So yeah, I mean, so this is why I can simply write it as UP. I mean, so. Okay. So now let's do the Euler equations for the DNLS. Just as a small addition here. So let's see. Okay, maybe I leave this here. That's very easy. So for the DNLS, I don't do any computations here, but remember that we have two fields, and we have this rho J, and we have the energy EJ. And now there's a computation, but it's not you don't need any details. The only thing is what you need is that the current, I mean either currents, I mean both currents are of the form I times C minus C complex conjugate. Okay, you know, I mean, so expressed in terms of the size, but when you look at these quantities, you see that you will find one term of a particular structure minus its complex conjugate. I mean, that's just a general feature of such type of equations. And then you do the average current. Well, you know, when you look at the e to the minus beta h, it's invariant under complex conjugation. When I do here the complex conjugation, I mean, then I pick up a minus sign, and therefore these things are sort of have to be zero. Okay, so for the DLNS, we find zero current, and there's actually no Euler equation whatsoever, right? I mean, just sort of want to point out that fine difference. Okay, you know what the consequences are. I mean, I have to discuss later, but just want to take that. You know, I mean, here I find non-zero currents, but you know, it really depends on the system. You have to look. I mean, there could be a situation where you know I just find at that stage zero currents, and then I have to think what else to do. Okay. All right. Now we don't have too much time, but let me nevertheless sort of go a little bit ahead, because you know there's more material, and so. So the next thing what we want to do is we want to come back to the quantity which we really want to study, right? I mean, I hope it's still on the board here. Here, maybe I should make a big sign here. So this is really. This is really what we want to study. And now let's do something totally trivial. Namely, let's say, well, look, I mean, now we have this macroscopic equation. And you know, if I start now from a state where I sort of make a local perturbation, I mean, you might think that I can, you know, the local perturbation, of course, here is something rather specific. I mean, here it's that particular local perturbation, but if I make such a local perturbation, you might think that it suffices to actually forget about all the details and hope that you know these Euler equations will give you already some information. But since we are doing a small perturbation, all what you have to do is you have to study these Euler equations in a very simple case, namely you have a uniform background plus a small local perturbation. Okay? So this is number 6, which is linearized Euler. Okay. Well, so you know the equation we have is ddt of u alpha plus dx. And so we always have 3 components, and now we have these currents. U alpha, the alpha current, which of course is some function. I mean, of course, I've written down the explicit function, but for this purpose, I mean, we don't really need that so much. I mean, so it's better to think of it in this form. I mean, this is just, and you have 3 of them, right? And then they depend on all fields, I mean, in a particular way. Okay? Well, so we want to linearize. I mean, then the linearized equation. Linearize, okay, so you linearize, okay, so there are many uses. I mean, that's part of this, the problem. I mean, so I have linearized the constant background. Constant background. I mean, which, you know, maybe I should call U0. I mean, so that's just sort of completely uniform. And then I do a small perturbation, and so I have to linearize this thing, and the small perturbation I call again U, because otherwise, you know, if I start to distinguishing, I mean, then it will become incomprehensible. So the linearized equation, and the background field is somehow completely dropped from the notation. I mean, you just have to remember that you know, at some stage I sort of pull it out of the head. I mean, everything will depend on the background which simply means that the background is fixed by saying that I want to compute this function at particular background values, right? I mean, so this is somehow fixed all the time. Okay, and so the linearized thing is that you have ddt of u. I mean, that's of course now a linear equation, and I write this as a. So I can write this as okay. It doesn't make any difference. I mean, where I put the a outside or inside. So let me write it like this: u vector is equal to 0, right? I mean, so this is now a 3 vector. This is a 3 by 3 matrix, and this is just a linearized equation up here. And of course, this is just the A alpha beta. You can sort of, it's just nothing else but differentiating these currents with respect to beta. You take the alpha current, and of course, you evaluate this at the background value u0, right? All right. Now, of course, the A we can compute in our case explicitly, so it's not very hard. You find the 1 here. So I'm just using these formulas from over here. 0. Okay. So maybe one other thing. You see, this is a system which is sort of Galilean invariant, and because the forces depend just on differences, and therefore the value of the average velocity is not very important. I mean, so of the background velocity, if you see, we're doing expansion, so I have to also know the value, the behavior sort of near the background value for small u. But for the background value, without any restriction, we can take the average velocity equal to 0, right? I mean, so for the background value, so maybe we put this here, background. Okay, so I guess I called this okay, so I called this u0. Okay, this is maybe okay. Anyway, so I did it already. Okay, so this is the second component of the background value, right? I mean, my list is always like over here. I mean, stretch, average momentum, and total energy. I mean, so it's the second component which I put simply equal to 0, right? Okay, and then the matrix will look like this. Okay, so it has a rather simple structure. Now here I get the partial derivative with respect to I. I get 0. Here I get the partial derivative with respect to E. And then I get 0, P, 0. Okay. So this is my linearized hydrodynamic equation. And now you wonder a little bit about this matrix. You see, maybe you would like to compute eigenvectors and eigenvalues and such type of things. But I mean, these are rather generic functions, and so maybe it's a very singular matrix. Okay, and so maybe well, I don't know if I can stop here, but maybe if I can use 3 minutes into sort of the last argument here. So you see, I mean, I guess what I was trying to say is that you may wonder whether how nice is this matrix actually, and there's a very generic argument which I would like to explain, namely which tells you that in fact this matrix is actually a very nice matrix, and of course it's sort of never symmetric, so to speak, but it has a nice system of right and left eigenvectors. And the point is, I would like to explain this because the argument is something which is extremely general. It doesn't rely so much. Of course, it relies somewhat on the underlying microscopics, but very little. Okay, so let me just sort of tell you how to do this. So the point is the following: that first of all, we need the susceptibility matrix, susceptibility, which I call C. Okay, so the C matrix is simply the static covariance matrix, right? I mean, so since in our case things are independent, it's just this property of a single site. I mean, so the susceptibility matrix simply means so it's the equilibrium correlations of the fluctuations in I Okay, and then you have here, I guess, well, we do this at zero background. So here you have zero, you have here the inverse temperature sitting. Okay, so here you have all zeros, and then you have sort of these cross correlations, fluctuations in R and fluctuations in the energy. Here you have the fluctuations. So these are second derivatives of your free energy, right? I mean, so. Okay. Symmetric matrix. Okay, so this of course is a nice matrix. I mean that's because we do thermodynamics, and thermodynamics is stable. It's a symmetric matrix, has positive eigenvalues. So this is of course, I mean this is fine. Okay, so the next observation is that there are some rules. Now there's a first sum rule which is very easy to understand. If I take this object here and sum it over all J. So you see, I take this object, I sum it over all J. This is a conserved quantity, so this should be independent of time. And so what is left over is only its value at time t equals 0, and so that's exactly what I've written down here. So this is equal to C. Okay. So this is just conservation law. Now there's a second sum rule. There are actually three sum rules, but today I will only do this one. So there's a second sum rule where I take the first moment of this matrix. Now you see there's a conservation law. So if I look at the time derivative, I will get the difference of carbons, and then I can do a partial integration, and so I get rid of this J, right? I just look at the time derivative of this quantity. I insert here the equations of motion. This is of a conservation type. So there will be a ddx appearing. I mean, on the lattice there will be a finite difference appearing. This finite difference I can partially integrate and get rid of, take the derivative of J, which is then just simply 1. Okay? Now when you do this computation, which is not difficult to do, is you find actually that's equal to AC times T. Okay. Now we also know stationarity. So you see this correlation function is stationary in both arguments. But you see when I shift these arguments sort of differ by their lower index. Okay? So what you find is that if I take S alpha and alpha prime of J and T, and this is so well, you can do it either way. I mean, you can okay. So I simply shift in both arguments, whereas here simply so I mean this J I shift over here, and this J I shift over here. Then of course it becomes a minus, and then it becomes a minus. But then I have sitting here the alpha prime. So this is actually equal to the S of alpha prime. So it's the transpose at minus J minus T. So that's the stationarity. Okay. And so what I can do now, I can take here now the transpose. Okay. So now I take the transpose of this equation. Okay, so when I take the transpose of this equation, and I use this formula, I get a minus J here. This sum gives me another minus J, but there's also a minus C here, so there's a minus C. So all what is left when I take the transpose is that I get the following identity. Namely, that this matrix is not totally general, but you find that AC is equal to AC transposed. And that's, of course, C. Now, C itself is symmetric, so this is the same times A transpose. And you see that I didn't use very much. I used the conservation law, and I use stationarity. I didn't use anything of, I mean, this is true, whatever system you look, I mean, as long as these two things are satisfied. Now, this tells you that the A is sort of conjugate with a very nice matrix, and that tells you that you have a nice system of right and left eigenvectors. It's not one of these funny matrices, you know, where you only have something sitting up here in the diagonal, and then okay, things like this. Okay. Okay. So you have right and left eigenvectors. And you have eigenvalues, and you compute the eigenvalues, and you find 3 of them. You find minus c, 0 c, and you find c squared is equal to minus drp plus p ep. Okay, maybe that's a good point to stop. Actually, I have a homework for you. Namely, you see the way I've written it is, I take here the square root. I mean, you know, I claim that this particular combination is always strictly positive, and that's the homework. I mean, how do you see this? Okay.
So somebody people are saying it's very go slow. Okay.
All right, so I'm already over time, so thank you very much.
Questions?